Welcome back, student, to part 2 of discussing Green's theorem. In this part, we will use Green's theorem to find this complicated line integral over a curve C, which is a closed curve in the region bounded by those two parabolas. So here we will use Green theorem. So we'll start by using Green theorem. So by Green's theorem, this line integral, which is b dx plus q dy, is equal. Of course, this will be my p and this will be my q. This will equal into double integral over the region bounded by this curve, partial q by partial x, negative partial p by partial y. Here we are assuming that the positive orientation is given counterclockwise. So this would be equal to double integral. Now we need to find partial q by partial x. So if we focus on this part, partial q by partial x, this is just a 2. Now if we focus in this part and we find partial p by partial y, the answer is just 1 dA. So the final thing is we need to find the integral d of 1 dA. Now in order to find this double integral, we need to sketch the region and we need to identify whether it is rectangle or it is type 1 region or it's type 2 region, or maybe we need to use the polar coordinates. So far, those are the 4 cases we have seen here. So we will use those 4 cases, and otherwise we have to do change of variables. But now let's sketch the region and see. Now my region consists of 2 parabolas, x equal y square and y equal x square. So if we open new page here, now here it is. This is y equal x square, and then the second one will be this one, x equal y square. Now the first thing we need to do is we need to find those intersection points up here. So how do we find the intersection points? Either we make the y equal the y. I'll do it in this side here. Intersection points. Either we make the y equal the y, so we will make the y in green equal the y in red. Now the y in orange, it's x squared. The y in red will be just the positive square root of x. If we take square for both sides, we get x4 equal x, which means x4 minus x equal to 0. If we take as x as common factor, we will get 2 real number answers here, either x equal to 0 or x equal to 1. So we know the intersection point are 0 and we know it is 1. Now we ask ourselves, what type of region do I have here? What type of region? Of course, we will assume it's positive orientation, so I'll do it in this way. Now what type of region? This is of course type, I will assume it is type 1 region, which means y between 2 functions and x will be between 2 numbers. The x is easy, it is between 0 and 1. We can see if we put any rectangle in the middle and we move it to the left, we reach 0. If we put a rectangle in the middle and we move it to the right, we get 1. So it's from 0 to 1. Now, if we put a rectangle, what is the top and the bottom of this rectangle? And that's exactly what we will have. The bottom is x squared, the function in orange. The top, the function in red, which is square root of x. And now we are able to find this double integral here, d of 1 d, which will be 0 to 1, and it will be from square root of x to x squared 1 d. Now this integral can be found 0 to 1. If we do this integral here in the inside, of course here I don't have dA, I should write it as dy dx. If we do this integral, this will be just x squared minus square root of x dx. And now this will give me x cubed over 3 minus x square root of x. This is x1 over 2. So if we add 1, we get x3 over 2, 2 over 3 from 0 to 1. And finally, this will be just negative 1 over 3. And that's what we get as an answer here. Oh, I'm sorry. I think I did kind of a small mistake here. I should switch those. That's why we get a negative answer here. So I get from x squared to square root of x. So this would change here by having x squared square root of x. And this one I can just change it into plus minus. So the final answer would be just 1 over 3. Thank you for watching. Please watch part 3 for the example number 3.